2.3 Introduction to Techniques of Differentiation. We finally get to learn some of those shortcuts for derivatives that you've been hearing about. Our first theorem tells us that the derivative of a constant function is 0. And that's easy to see. As we know, derivative means slope, and the slope of any constant function is always 0. Down below we see some examples. The derivative of y equals 1 is 0. The derivative of y equals negative 3 is 0. The derivative, or slope, of y equals pi is 0. And so on. Any constant function, the derivative is always 0. Our next formula tells us the derivative of power functions. Start off with a simple one. The derivative of y equals x. We know that the slope is 1 because this is in y equals mx plus b form. In this particular problem, the slope is 1. In general, if we have x to the n power, the way we're going to find the slope of that curve is we drop the exponent. Give an example as I go here. You drop the exponent, and then lower the exponent by 1. That's all you do. So I drop the 10 down, lower the 10 by 1 to 9. Down below we see 3 examples of that also. Derivative of x to the 4th, 4x cubed, and so on. Take a look at all 3 of those. Make sure you understand how we get those results. Turns out that's true whether that exponent is a whole number or any other number, as long as it's a real number. So we could have something like, as we see below, when we want the derivative of x to the pi, drop down the pi, lower the exponent by 1. So the exponent becomes pi minus 1. Next one's a little more interesting. Derivative of 1 over x. We first rewrite 1 over x as x to the 1, negative 1. Then we can drop that negative 1 down and lower the exponent by 1. So we end up with negative x to the negative 2, or written simplified, negative 1 over x squared. Same idea works for any exponent on the bottom. 1 over w to the 100th. First rewrite it as w to the negative 100. Drop the negative 100. Lower the exponent by 1. Then rewrite. Also works with a fraction, as you see in the next piece. On the last piece, cube root of x, you have to get a little more creative. You have to first rewrite that as x to the 1/3. Then you can drop the 1/3 down and lower the exponent by 1. And if you're having trouble going from here to here, you need to see me. That's an Algebra 2 skill that we should have mastered. Go ahead and pause the video, look over all these, make sure you understand each of the examples. They're all using the same rule. Next up, we're told that if we have a constant times a function, we could just pull that constant out and then take the derivative of what's left. Basically what we want to do. So for example, if we have something like the derivative of 4x to the 8th, first we could take the 4 out and then take the derivative of what's left. We know the derivative of x to the 8th is 8x to the 7th. Multiply that by the 4, we get our answer. And that works with any constant that we put in front of a function. Go ahead and try following along those next 2 examples. Make sure you understand each step of the way. If not, get some help. The next theorem tells us something else that we like. It says if we've got 2 functions added together and we want their derivative, we can just take the derivative of each piece separately and add the answers together. Same thing works for subtraction. If we have 2 functions that are subtracted and we want the derivative of the whole thing, we just take the derivative of each piece and subtract them. So in our next example, we see a bigger function, 2x to the 6th plus x to the 9th. We break that into 2 smaller pieces that we know how to find the derivative of, and then add those answers together. And we're done. The second one, the one below, is a little trickier. Notice they split this up. The step they're not showing is they're rewriting it as square root of x over square root of x. minus 2x over square root of x. And from there, you should be able to get to this step easily enough. Then you split it up into two functions, find your derivative. If you're having trouble going from one step to the next, bring it to my attention, we'll talk it through. You should be able to follow that algebra. So we've got an example that we're going to try here. Using the skills you know, try this one on your own, see if you get the same thing I get. That's it. One thing to point out, dy dx is just same notation, it means derivative. Other ways we can write derivative, these are all worth knowing. Some equivalent terms, dy dx is the same thing as y prime, that's y with an apostrophe, which is the same thing as f prime of x. You'll see all three of those notations throughout any math book. Example 7 says, at what points, if any, does this graph have a horizontal tangent line? Think about what it means to have a horizontal tangent line. Specifically, what slope do we have to have if we have a horizontal tangent line? Think about that for a few seconds. If you thought that our slope must be 0, you'd be right. So we want to find our slope equation, which happens to be called the derivative, which we should be able to get easily enough. And we want that slope to equal 0. So we have to say 3x squared minus 3 equals 0. That you should totally be able to solve on your own. Do that, and we'll talk about what we're going to do with our result. We got the values x equals -1 and x equals 1, which matches up with the points we see on our graph. Those are the two places where the slope is 0. But it's asking us for the points, so we need to actually figure out those points. So we're going to go plug -1 and 1 back into the equation, not into our slope equation, not this one. If we plug into there, we should get 0. That's what we just figured out. If we want the point on the graph, we've got to go plug back into this guy. And once we go back and do that, we get 1, 2 and -1, 6, which matches up with our graph, a y value of 2 and a y value of 6. We should be able to do all that without looking at the picture of the graph. The graph's just there right now to make life a little easier. Example 8 is a tricky one. Go ahead, pause the video, read over it for a moment before we move forward. Problem says we're going to find the area of the triangle formed from the coordinate axes, that's the x-axis and the y-axis, and the tangent line to this curve that we see. So we're given a curve, except we should be able to do this without looking at the graph. We'll talk about that. And this picture even gives us the tangent line. It shows us a picture. So if we were given the picture, we should be able to say, oh, this is a triangle with height 2, base 5, so the area is base times height over 2. And we'd be done. The trickier part is, what if we're not given the picture? We'd have to kind of come up with our own picture. We're given one of the points on the axis, 5, 0. What we're not given is the y intercept. That's what we got to figure out. And to figure that out, we need to find the equation of the tangent line. That way we can see what the y-intercept of that tangent line is. And of course, to find the equation of the tangent line, we need two things. We need a point, which we're given, and we need a slope, which we're not given. Fortunately, we're all experts at finding derivatives now, so we can find the derivative of this particular function. Pause the video, try that on your own, see if you get the same thing as me. Just looking for the derivative right now. Once we've got our derivative, we can find the slope at a particular point by plugging in whatever number we want. In this case, we want x to equal 5. So y prime of 5 would equal Negative 5 over 25 minus 1/5 becomes negative 2/5. And remember, my whole goal right now is to find the equation of the tangent line. Once I know the equation of the tangent line, I will be able to find out exactly where that y-intercept is. So I go through my point slope formula. Y minus y1 equals m. We know what m is. X minus x1. If you're not sure where I got this x1 and y1, look back up at the original problem. We end up with y equals negative 2/5 x plus 2. So we now have our y-intercept, 0, 2. That's enough information to help us find the area of this triangle. Notice we're back to this same triangle, but we figured it out without being given the picture. Now we could go base times height divided by 2, and we get our 5. That's kind of a lot of work, and you have to really understand what you're doing and why you're doing it. Maybe go back and watch this example again if it didn't quite make sense. Our plan of attack was figure out where this tangent line touches each axis, and then find the area of that triangle. That was the basic problem. To get there, we had to use derivatives and equations of lines. Our last example for this section is something called higher derivatives. We know how to find the derivative of a function. Turns out you can find the derivative of that, and then the derivative of that, and you could keep going on forever. So for instance, we can get a first derivative. Once we know our first derivative, use the same process to find the derivative again. That's called the second derivative, third derivative, and so on. Notice with a polynomial, you're eventually going to get to 0. That's only true with polynomials. You don't always get to 0. Soon we're going to be learning how to find derivatives of things like trig functions, logarithms, exponents. Those won't go to 0 eventually, but polynomials always will. The reason that is, look what happens to our degree every time. If we start with a 4th degree, our derivative is a 3rd degree, then the degree keeps going down by 1 until you have nothing left. Go ahead and pause the video and try this guided practice on your own. That's it for this exciting shortcut lesson. More to come tomorrow.